Try this for a second. Picture the solar system. You probably saw a small yellow circle with a few dots orbiting it, maybe rings around one, maybe a little blue marble labeled Earth. That image is wrong, not slightly wrong, catastrophically wrong. And the reason it's wrong reveals something strange about the human brain, something that has nothing to do with space and everything to do with the machine sitting behind your eyes right now. Here is the strange part. Your brain was never built to understand size on this scale. It evolved to judge distances across a savanna, not across a galaxy. And when something is too big for the tool you're using to measure it, the tool doesn't fail quietly. It fails by lying to you smoothly, convincingly, without ever telling you it's lying. Let's start with the model you probably grew up with, the one in textbooks and posters, the sun as a circle a few inches wide, the planets as small dots spaced out evenly beside it, almost touching. That model is a lie of convenience. To draw the solar system at true scale, if the sun were the size of a basketball, Earth would be a grain of sand sitting about 30 yards away. Neptune, the most distant planet, would be over half a mile from that basketball. On that same scale, the nearest star beyond our sun wouldn't even fit on the same continent. It would be roughly 4,500 miles away. Take a breath, that's not a typo, that's the actual ratio. Your brain cannot hold that ratio, not because you're not smart enough, because no human brain can. This is the conclusion of decades of work in cognitive science on what researchers call scale cognition, the study of how humans understand sizes and distances that exceed direct sensory experience. Psychologist Carrie Marsh, along with several colleagues studying scale reasoning, has shown that people consistently and dramatically underestimate exponential differences in size. Ask someone to compare a millimeter to a meter, then a meter to a kilometer, and most people treat both jumps as roughly similar in magnitude. They're not. The second jump is 1,000 times larger than the first. Your brain doesn't process that difference. It just sees bigger and much bigger and treats them as cousins instead of strangers. Now stretch that error out to cosmic distances, and the failure becomes almost total. When you hear that a star is 4 light-years away, your brain hears a number, a label. It does not actually compute that light, moving at 186,000 miles every single second, the fastest thing that exists, would still take 4 years to cross that gap. Your brain doesn't simulate that. It can't. There's no internal model fast enough or large enough to run it. So what does your brain do instead? It substitutes. This is one of the most well-documented patterns in cognitive psychology. When a question is too difficult to answer directly, your brain quietly swaps in an easier question and answers that one instead, often without telling you the swap happened. Daniel Kahneman, the psychologist whose work on judgment and decision-making reshaped how scientists understand the mind, called this substitution one of the central mechanisms behind human intuition. Applied to space, the substitution looks like this. You can't actually picture a light year, so your brain quietly swaps in something familiar, a long car ride, a long flight, multiplied a few times in your head. The result feels like an answer. It is not. It's a guess dressed up as understanding. This is why most people, when they look at images of the solar system, feel like they get it, even though what they're picturing is wrong by a factor of thousands. The feeling of understanding and the actual accuracy of understanding are two completely separate systems in your brain, and for cosmic scale, they have almost nothing to do with each other. Now go bigger. Our entire solar system, Sun, all 8 planets, every asteroid and comet, sits inside the Milky Way galaxy. The Milky Way contains an estimated 100 to 400 billion stars. If you tried to count them one per second without stopping to eat, sleep, or pause, counting only the low estimate of 100 billion, it would take you more than 3,000 years. And the Milky Way is one galaxy. Observations from the Hubble Space Telescope, later expanded by data from the James Webb Space Telescope, suggest there are over 100 billion other galaxies in the observable universe. Some estimates push that number past a trillion, once the faintest, most distant galaxies are accounted for. You are not failing to grasp this because you lack imagination. You are failing because your imagination runs on hardware built for tracking herds of animals and counting the members of a tribe, not for holding trillions of anything in conscious awareness at once. Astrophysicist Neil deGrasse Tyson has often pointed out that the universe doesn't care whether your brain can comprehend it. Scale doesn't bend to accommodate human intuition. The universe was never built to be relatable. So here's the deeper question. If your brain can't actually picture cosmic scale, what is it doing instead every time you think about space? It's running a translation, a simplification, a cartoon. And in a strange way, that cartoon might be the most human thing about how you relate to the universe. You don't experience the actual scale of the cosmos. You experience a story about the cosmos, compressed down into something your mind can hold without breaking. This isn't a flaw unique to space. It's the same mechanism at work when you think about deep time, evolution measured in millions of years, or population numbers in the billions. Your brain takes the incomprehensible and shrinks it down into something it can carry, not because it wants to deceive you, because it has no other option. But here's where it gets interesting. Some people have actually had a glimpse past that compression. Astronauts who view Earth from orbit, or from the surface of the Moon, often describe an experience researchers now call the overview effect, a documented and studied shift in perspective triggered by directly perceiving the planet as a small, finite object suspended in vast emptiness. Frank White, who coined the term, interviewed dozens of astronauts and found a consistent pattern. They didn't just learn a new fact. Something in their actual felt sense of scale shifted, even temporarily breaking through the comfortable substitutions the rest of us rely on every day. Most of us will never see that view directly, but you don't need to leave the ground to feel a small piece of it. Try this. The light entering your eyes right now from the nearest star beyond our sun left that star's surface more than 4 years ago. It traveled in a straight, unbroken line for 4 years, through emptiness, with nothing to slow it down, only to land for a fraction of a second on your retina, in this room at this exact moment. You're not just looking at a star. You're looking at a 4-year-old message that has been traveling specifically toward you for longer than some friendships last. That's not a metaphor. It's physics. And maybe that's the closest thing to truly touching the scale of the universe that a human brain, built for savannas and tribes and short distances, can ever actually do. Not by comprehending the whole picture. By catching for 1 second a single real piece of it, exactly as it is. So the next time you picture the solar system, picture the basketball. Picture the grain of sand 30 yards away. Picture the nearest star 4,500 miles past that. It will still feel wrong. It will always feel wrong. But now at least you'll know why.